In this lecture we will discuss Michael addition, also known as conjugate addition. Take a simple aldehyde or ketone. When we add a nucleophile on electrophilic carbonyl carbon, the weak pi bond breaks towards more electronegative oxygen. This forms tetrahedral alkoxide intermediate with negatively charged oxygen. The next step is the protonation on oxygen to form the alcohol product. If we compare this product with reactant, we can clearly observe that hydrogen and nucleophile have been added on adjacent carbons, marked here as 1 and 2. This type of addition reaction on adjacent atoms is called 1,2 addition reaction. Now, if a pi bond is added to this aldehyde or ketone, between alpha and beta position, this makes alpha-beta unsaturated carbonyl compound. Such a pi bond is in conjugation with carbonyl group, so that various resonance structures can be written like this. In these structures, the positive charge can be seen moving from carbonyl carbon to beta carbon. Therefore, resonance hybrid can be written like this, with a delta positive charge on carbonyl carbon and beta carbon. Thus, nucleophile can either approach the carbonyl carbon or beta carbon, creating two possible pathways. In the first pathway, the nucleophilic addition can be shown to occur on carbonyl carbon, just like we have shown in the case of simple aldehyde or ketone. The weak pi bond breaks towards more electronegative oxygen to form alkoxide. This is then protonated on oxygen to form alcohol. In order to show the location of added atoms or groups, we can number the atoms like this, 1 to 4, but remember this numbering is not as per IUPAC rules. Notice that H and nucleophile have been added on the adjacent atoms, 1 and 2. Therefore, just like in the case of nucleophilic addition on simple aldehyde or ketone, we call this as 1,2 addition or direct addition. In the second pathway, the nucleophile can approach the electrophilic beta carbon, so that pi bond moves between alpha carbon and carbonyl carbon, which in turn breaks the carbonyl pi bond towards more electronegative oxygen, making it negatively charged. This type of compound is called enolate. Just like before, this can be protonated on oxygen to form enol. Again, we will number the atoms to trace the location of atom or groups added. It is obvious that H and nucleophile have been added on 1 and 4 positions. Therefore, such addition is called 1,4 addition reaction. The enol form, being less stable, quickly tautomerizes into keto form. We will now discuss the reasons behind the direct versus conjugate addition. Or in other words, we can say 1,2 addition versus 1,4 addition. 1,4 addition of enolate on alpha-beta unsaturated carbonyl is called Michael addition. The type of addition depends upon the reversibility of the nucleophilic addition. In case of simple aldehyde or ketone, the reversible addition is shown with 2 arrows, and the irreversible addition is shown with a single arrow. In both cases, the same alkoxide is formed. In case of alpha-beta unsaturated carbonyl compound, the reversible addition of nucleophile followed by protonation at oxygen gives conjugate addition product. Whereas in case of irreversible addition, direct addition or 1,2 addition product is formed. Now the question is, which nucleophiles add reversibly and which add irreversibly? Nucleophiles that add reversibly are hydroxide, alkoxide, amide, halides, carboxylate, cyanide, carbanion attached with electron withdrawing groups called as enolates, enamines, thiols, thiolates, organocuprates also called Gilman reagent. Nucleophiles that add irreversibly are Grignard reagent, organolithium reagent, hydride-producing reagents like lithium aluminium hydride and sodium borohydride, Witting reagent, and other nucleophiles having strong or negative anhydride reagents. Thus, nucleophiles that add reversibly give conjugate addition, whereas those that add irreversibly give direct addition. And remember that conjugate addition produces thermodynamic product, whereas direct addition gives kinetic product as major product. Thermodynamic product is stable product, because this product has greater total bond energy compared to kinetic product. The kinetic product is formed faster than thermodynamic product, because in this case, nucleophile adds to more electrophilic carbonyl carbon, compared to less electrophilic beta carbon, in case of conjugate addition. Thus we should remember, if the nucleophile adds reversibly, then the reaction takes place under thermodynamic control and the major product is the thermodynamic product, that is, the one that is more stable. If the nucleophile adds irreversibly, then the reaction takes place under kinetic control and the major product is the kinetic product, that is, the one that is produced more rapidly. The conjugate addition product is the one that is more stable, making it the thermodynamic product. The direct addition product is the one that is produced more rapidly, making it the kinetic product. Why is the conjugate addition product thermodynamically more stable product? First reason is charge stability. The conjugate addition product is more stable in part because of charge stability. Notice that the immediate product of conjugate addition is an enolate anion, which, as shown here, has a resonance-stabilized negative charge. On the other hand, the direct addition product is shown here, possesses an isolated negative charge, and is therefore less stable. Second reason is bond energy. The overall uncharged product of conjugate addition has greater total bond energy than the one produced from direct addition. The greater total bond energy in the conjugate addition product comes primarily from the type of double bond present. As shown here, the conjugate addition product has a CO double bond, which, on average, is 101 kilojoules per mole stronger than the CC double bond in the direct addition product, hence making it more stable. We can show the direct and conjugate addition in terms of energy profile diagram. The blue curve represents direct addition, whereas the red curve represents conjugate addition. The energy barrier is lower for direct addition because, in the transition state, the nucleophile is attracted more strongly to the carbonyl carbon than to the beta carbon. Thus, direct addition gives the kinetic product. However, the immediate enolate formed in conjugate addition is resonance stabilized and hence more stable than the isolated negative charge in alkoxide formed in direct addition. Thus, the more stable product is formed from conjugate addition, so conjugate addition gives the thermodynamic product. If a carbon nucleophile adds via conjugate addition, thereby forming a carbon-carbon bond, the process is called a Michael reaction or Michael addition, after the American chemist Arthur Michael. Over the years, however, the term Michael reaction has evolved into a generic description of conjugate additions involving any nucleophile. Highly stabilized enolates are good nucleophiles for Michael reaction and are called Michael donors. The alpha-beta unsaturated carbonyl compounds are called Michael acceptors. A variety of Michael donors and acceptors are observed to react with each other to produce Michael reactions. Some common examples of Michael donors and acceptors are given here. Any one of the Michael donors in this table will react with any one of the Michael acceptors to give a 1,4 conjugate addition reaction. With this in mind, let's now explore the outcome of some reactions. In this example, the starting material is an alpha-beta unsaturated cyclic ketone, which can function as a Michael acceptor. The reagent, lithium diethyl cuprate, as we now know, adds reversibly and therefore gives conjugate addition. Therefore, this can function as a Michael donor. As such, we expect a Michael reaction. Thus, ethyl group of Gilman reagent approaches beta position of alpha-beta unsaturated ketone. The result is formation of resonance-stabilized enolate ion. This is protonated on oxygen to form enol, which then tautomerizes to more stable keto form. In this second example, the starting diketone has an acidic proton which is removed upon treatment with hydroxide base to form a highly stabilized enolate ion, which then serves as a Michael donor in a 1,4 conjugate addition. The enolate ion attacks the Michael acceptor alpha-beta unsaturated aldehyde to form another enolate ion. This is then protonated on oxygen upon acid workup to give enol, which tautomerizes to give a more stable ketone form as product. The third example is similar to second one we just solved. The diketone has acidic methylene protons which will be abstracted by hydroxide base to form doubly stabilized enolate ion that acts as Michael donor. This will attack beta carbon of Michael acceptor alpha-beta unsaturated ketone to form enolate ion that will then be protonated on oxygen to form enol, which then tautomerizes to more stable keto form to give the product. In this fourth example, the CN group has the polar pi bond which is in conjugation with CC double bond. The nucleophile is methoxide anion, which adds reversibly to give conjugate addition. This methoxide anion adds on beta carbon to place negative charge on nitrogen in this case. This is then protonated on nitrogen to form enol-type compound. Which then tautomerizes to reform CN triple bond. In this example, the ketone is first converted to an amine upon treatment with secondary amine. The enamines, we know, adds reversibly to give conjugate addition product. Thus, enamine adds on the beta carbon of the alpha-beta unsaturated ketone to form an intermediate, that is both an iminium ion and an enolate ion. Upon acid workup, both groups are converted into carbonyl groups. The iminium ion undergoes hydrolysis to form a carbonyl group, and the enolate ion is protonated to form an enol, which tautomerizes to form a carbonyl group. By now we understood that alpha-beta unsaturated ketone or aldehydes gives direct addition product with Grignard reagent and organolithium reagent. But with organocuprates, thiols and cyanonucleophiles, it gives conjugate addition products as major products. In this example, the alpha-beta unsaturated ketone and the nucleophilic amine group are present in the same molecule. The amino group adds at the beta carbon intramolecularly to form this enolate ion that also has positive charge on nitrogen. In the next step, the oxygen is protonated intramolecularly, which is lost from positively charged nitrogen. The enol is formed, which then tautomerizes to more stable keto form. Thus, this is an example of intramolecular Michael addition.